Hey there, time for day 20. Getting kind of burned out. Hoping this one's easier than yesterday. All right. You know they're headed to the grove where a starfruit grows, so if you can figure out where it is, you should be able to meet back up with them. Fortunately, your handheld device has a file, your puzzle input, that contains the grove's coordinates. All right. While you were still back at camp, you overheard some elves talking about coordinate file encryption. Mixing. Encrypted file is a list of numbers. To mix the file, move each number forward or backward in the file a number of positions equal to the value of the number being moved. The list is circular, so moving a number off of one end of the list wraps around to the other. To move one in a sequence like this, the one moves one position forward. To move -2, it moves 2 positions backwards. Okay. That doesn't seem like 2 positions backwards. That looks like 3 positions backwards. Because wouldn't the front be the first and then the back be the second? Numbers should be moved in the order they originally appeared in the encrypted file. Numbers moving around during the mixing process do not change the order in which the numbers are moved. Consider this. This is our file. One moves between 2 and -3. 2 moves between -3 and 3. -3 moves between -2 and 0. Linear grove coordinates can be found by looking at the 1000th, 2000th, and 3000th numbers after the value 0, wrapping around the list as necessary. 1000th number after 0 is 4. What is the sum of the 3 numbers that form the grove coordinates? And what does our puzzle input look like? A rather giant list. A rather giant list. All right. So the -3 was here. So if I was going to say, where should it go? That would be 1. And apparently that's 2 and that's 3. I guess the beginning and the end are considered equal. And the grove coordinates can be found by looking. Okay, so how big is our real data? That might influence how we do this. All right, so there's 5,000 numbers in the real list. Okay. What is the easiest way to keep track of this? We have to move them in the order that they originally appeared in the encrypted file. Nobody said anything about them being unique either, right? I'm curious. Console write line. Let's see. So this is just going to be an int parse. Console write line. Data count. Console write line. I guess it's length, isn't it? Because it's an array. Data unique. Isn't unique? It's distinct. Of course, that's count. Right, so they're not distinct. That makes sense. So you can't just go looking for it. Um, hmm. And if you want to keep track of where you're supposed to be, you can't necessarily just track 5,000 indices. I mean, I suppose you could. So 1,000th after the 0. So that's 1, 2, 3, 4, 5. So you want the 1,005th. All right. 1,005 divided by 7. 143 times 7. So the fourth number, right? 1, 2, 3, 4. The fourth number. Okay. What is going to be the best strategy? What is going to be the best strategy? Sum of three numbers of form graph coordinates. Could do this as a there is no really is no doubly linked list in .NET, is there? Not that I know of. New window up here. A doubly linked list, C#. Oh, there is a linked list of T. Add after, remove. So everything's tracked to the linked list node of T. So when you add, you get back a linked list node of T. Oh, you make linked list nodes of T. Okay. Sure. So we're going to do a new linked list node of int of that. All right. And then originals is going to be dated at toLinked list. Actually, it doesn't. Actually, leaving it there is fine, right? What we need is we need to just convert this into a list for each item in data. Let's see. So this is our linked list. Linked list event. Linked list add last item. right? And then we're going to say for each item in data, so we need to know, so given a linked list item, what do we know about it? Item, we should be able to go back and forward, right? Previous and next. And that can return null because it's not circular. So move quantity is going to be item.value mod data length, right? Because you only have to move it as many as, like if you have to move it, let's see, let's say we had 7, right? And you were right here and you were 7, you'd be 1, 2, 3, 4, 5, 6, wrapped around a 7, yes. So that makes sense. Okay. We're going to find your, see, we need to find the one that you're going to be after. Is that right? Linked list, add, we can do add after or add before. Do add after or add before. Okay. Let's see. So if we want to do, let's see, if move quantity is greater than 0, else we do this, right? So if we want to move forward, then we're going to go ahead and find, say, in between. Is that how they phrased it? Is in between? Let's see. Talking about number of positions equal. Well, so moving a number off of one end of the list wraps it back around to the other end as if the ends were connected. So I guess it doesn't really matter because the front of the list and the back of the list are exactly the same, especially as they relate to the position of 0. So we'll do before is going to be item previous or linked list last, right? And then, so we want to print this out, right? So we're going to go ahead and print the list, linked list. And then after we're done with everybody, we're going to print it again. All right. Console write line, probably just string join commas on the list. It's probably good enough. And then so while move quantity is greater than 0, before is going to be equal to No, see, that's bad, right? Well, we're going to do after. We want to look at after here. That makes it easier. So we want to decrement because we've already moved one. If move quantity is less than 0, because I don't want to do anything dumb with 0. Moved item value. All right, and then you can be initial. So while we have more to move, then after becomes after next or linked list first. So I think that's it. And you're telling me you may be null, but really you never will be, because this list is never empty. And then we're going to say linked list remove our item, and linked list add after, no, add before, because that's the item that's after us. So add before item. Sorry, add before after item, and it's fine. So this is the same thing, except it goes in reverse. And we go with previous, and we wrap around to the last, and we say while you're less than 0, then before is before previous, looking for the last, then we remove, and then we add after the before. All right, let's see how that works. All right, so given that, we have this. So there's our initial. Then after we moved 1, and that didn't move at all, did it? Oh, this list is not. Oh, yeah, I shouldn't be decrementing first. I should be decrementing after. I had that wrong. Okay, let's try that again. Whoops, don't double click. All right. 2, 1, -3. Yep. 1, -3, 2. Yep. Let's go to the end. 1, 2, -3, 4, 0, 3, -2. That looks good. And then here, what we need is we'll grab result and we'll come down here and we'll basically say, linked list, can we index into it? It is an I collection, so we can index into it, and it has a count. Okay. So let's see, index of 0 is going to be linked list dot index of. We don't have an index of. Well, we can find the 0, right? The zero node is going to be data where the node value is 0, right? That's going to be one of those. And then we can take the 0 node and figure out how many times we need to move. So let's see. Move count is going to be 1,000 mod linked list count. And then we're going to say, well, move count double minus is greater than 0. Target node is 0 node. Target node is target node next, or target or the list first, right? And then let's console write line target node value. Yeah. So the target node value is 4. I believe that was correct. So 4, -3, and 2. So we're going to do that 1,000, 2,000, 3,000. 1,000, 2,000, 3,000. So you can just be that. So for int I is 0, I is less than 3, double plus I. We've got a move count. We move it. And then result plus equals target node value. And then we're going to return the results. That should get us 3. It does. Okay. So let's comment these out. And let's comment these out. And let's get our big list. Let's get an answer, 8372. 8372. Okay, part 2. Guard coordinates seem nonsensical. While you ponder the mysteries, you suddenly remember the rest of the decryption routine. All right. First, you need to apply the decryption key. Multiply each number by the decryption key before you begin. This will produce the actual list of numbers to mix. Second, you need to mix the list of numbers 10 times. The order in which the numbers are mixed does not change during the mixing. The numbers are still moved in the order they appeared in the original pre-mixed list. So if -3 appears 4th in the original list. So basically, I don't think I see any numbers here that are bigger or smaller than 10,000. All right. Yeah, they're all sort of smallish. So that's fine. So here we're going to do var new data is data select new, let's see, new linked list node of long, because now they're longs, right? D.value times this to array. Okay. And so they're going to say after 10 rounds, so they're going to print out after every round, which is fine. So we're going to grab this, right? I don't know what they actually are asking for the result. We'll get there in a second. So your linked list of long, right? And then new data. Size of the list doesn't change, just the, yeah. none of the math should be different. So they're printing it out after every list. So let's do that. So let's console write line initial print the list, which you can just be a list of T. Print the list of T. Nobody cares because it's fine. So print the list of linked list, right? For int I is 0, I is less than 10. We have to do this, right? Because that's what I said, was 10 rounds, right? 10 rounds, and then console write line after round I plus 1. Print the list. Okay. Now what are we doing here, which is Grove Corner still found the same way. So 1,000th, 2,000th, 3,000th. Target node is, this is new data, not data. So that should be the same. Yep, that should be the same. Okay. Yep. Okay. Let's see if we ended up with the same shape. So they have 0 at the front and I have 0 at the end. That's irrelevant. But actually the rest of this looks wrong now. So all the math looked okay. Move quantity should be along now. It is. Mod data length. That should still be true though, right? So like, what is this? So what is that? Mod 7. That's 4, so it should move 4 positions, right? 1, 2, 3, 4, so it should be here. No, it should be here. Oh, well, of course, we're not seeing it all, are we? So let's do 1. And then here, console write line. Right, and then we're going to say write line moved. Let's see, moved. Moved item value, the actual move quantity. And then we're going to say print the list. The list is linked list. See if we can figure out what's going on here, right? So you should have moved 4 spaces, which would put you 1, 2, 3, 4. So put you right before the 0. Yeah, that looks good. And we move you 1 space, which then puts you over there. We move you -5 spaces. I mean, not that I don't trust the math, but we'll go ahead and consult the calculator again, right? Mod 7 is 2. which I guess is the same as -5, isn't it? Which means I didn't need to do backwards and forwards. Although we are preserving the mod function here, right? So -5 and 2, those are the same thing, sure. Which means this one needs to have gone 1, 2, 3, 4, 5. So after that, none of that looks wrong, but then after one round, we end up with something different, didn't we? Quite different. Why? How? After one round of mixing, yeah, we have something quite different. Multiply each number by the decryption before you begin. This is the actual numbers to mix. Second, you need to mix the list of numbers 10 times. The order in which the numbers are mixed does not change. The numbers are still moved. So if negative appears fourth, number 3 would be the fourth move during each round of mixing. So it implies that the rounds of mixing run sequentially. But what if they don't? Actually, after one round, it wouldn't matter because sequentially or, oh, yes, it would. Yes, it absolutely would. Yeah, and then that, all right, well, let's see what that does. We're gonna comment out these because that's too much printing. No, see that? No, I mean, clearly the way they're printing it out, this obviously has to go like this. I just don't understand how we get everything so different. Oh yeah, stop the move print. Because if we had like one round should be exactly the same algorithm, right? One round should be exactly the same algorithm, and then we end up with completely different. Numbers are still moved in the order they appeared in the original pre-mixed list. So if -3 appears there, by the way, we didn't get the right answer, right? Okay, we didn't get the right answer, just checking. Not that I would have expected us to. I really don't understand how this could be so wrong. The algorithm is correct. What am I missing? Apply the decryption key. Multiply each number in the decryption key before you begin. I got the right numbers, right? Let's pretend like I don't actually want to do this. This is going to be really expensive, but let's go ahead and let it do its thing, right? It's going to be slow, but is it going to run quick enough to get me an actual answer? Doesn't look like it. I'm not surprised. It is kind of interesting that sample data, well, so there's 5,000 of these. There's definitely numbers in here that are bigger than 5,000. So if the mod part of the algorithm was wrong, we would have definitely seen it. Move quantity, previous, last. I'm going to add after. Yeah. How is this wrong? Oh, this is new data length. Not that it matters. All right. It's going to be the same size. We'll come and select data and make sure we don't have anything highlighted down here in part 2. Not that I would have expected it to. The modulus isn't weird because of this being an int, is it? I wouldn't think so. You're telling me cast is redundant. Okay. I really don't understand how that's... One, two, three, four. That's where that landed. So you're 1, 1. That's where you landed. So you're -5. So that would be 1, 2, 3, 4, 5. And that's where you landed. So you would be 4. So you would be 1, 2, sorry, 5. Right? So you would be 1, 2, 3, 4, 5. How is that? How is moving 5 not moving? That can't be right, right? Where we're there. 1, 2, 3, 4, 5. One, 2, 3, 4, 5. It helps if you count correctly. So -16 goes 1 back. So you go here. 0 doesn't move, so the list is the same. 32K moves 2. So that's 1, 2. Whoops, where was 32K? Up here, 32K. So that's 1, 2. So yeah, you're in between there. And then after one round, this is what it is. Hey, I mean, everything looks right. But everything looks wrong. Well, I'm going to try running it with the real data and see if maybe the sample is wrong. at which point I'm going to be really upset. Oh my God, stop printing things. Yeah, stop printing things. Well, that's interesting. How is that possible? What line was that on? That was on 93. Add before, after. How is after not? Oh, you know what? Is it possible I need to remove myself from the list first? Why did I not? Ooh, how did everything work before with me not doing that, if that's the case? Negative 3,000. This is the sample data, right? No, see, that's still wrong. And if I was supposed to remove myself, then the move quantity would be 1 less the length minus 1. If that was the case. Wow, talk about really second guessing yourself here. Right? Because I mean, I guess you have 1, 2, 3, 4, 5, 6 gaps. Well, 7 gaps because of the round. But when you take 1 out, you have 6 gaps. Wow. I still get 3 up there. Oh my God. So there's 243, 1681. So yeah, we're definitely not in the right place either. And yet I still got 3. Did I do everything correctly here? Holy smokes. Did I really get it like accidentally wrong? The answer is 1623 something or other. Whoops, why am I scrolling there? 1623 something or other. Wow, I got it wrong. That's amazing. All right, let's stop printing things out. And then stop printing things out. This big giant number. Wow. Yeah, talk about accidentally getting part 1 correct. Wow, that was unexpected, let me tell you. In terms of cleaning up, I don't think there's really a whole lot to clean up here other than obviously we could mix, right? We could set mix up as its own function. And then the count here is exactly the same as well, right? So we could do mixes here. So let's do mix once with length list of long, length list. And then, yeah, don't care about that because I'm about to make you guys all longs as well. And I don't need print anymore. You are going to be this and this for just a moment. So this is mix, this is data, this is data. Mix the linked list. I don't need new data. How do I make the linked list up here? Oh yes, I just did the same thing. Okay, so mix it 10 times. That's our target node. And then we do this. Return compute results for our linked list. Long compute results for linked list of long. Linked list. All right, so that's our compute result. 2039. Really? That's interesting. Oh, I wouldn't have expected that. Like, let's go back here. We'll leave you commented out because in theory, you're necessary. So there's 3. Linked list node already belongs to a linked list. Oh yeah, that's probably true, isn't it? Can't reuse those, can we? So let's do this then. We'll just do long parse the line. You'll be an array. And we'll say the nodes are data select new linked list node of long for the data to array. And then we mix the nodes into the linked list. We compute the result nodes linked list. All right. We need the nodes here. I don't think we do actually. Oh, yeah, we do. Yeah, okay. Linked list node long nodes. That's going to be nodes. Right. And then back to nodes. So when we see data, data length is fine, except this is nodes. And then let's see if we get number 1 back to normal. Turn 0 for the moment. Linked list node does not currently belong to a linked list. Yeah, that's interesting. So mix. So those are the nodes. I don't know, part 1, why you're all the way up there. You should be down here. Oh, that's too much. You should be down here. nodes, make linked list nodes, and then make a linked list. Okay, I knew that. So there's 3. And we need this. Right, and then we mix the nodes. And then we compute the result. By the way, it's possible the linked list class gives you access to the nodes. Or not. No, not quick and easy. Otherwise, it'd be a property, which means it'd be up top. 2. Sorry, why 2? Right, this needs to be multiplied. We're back to the problem again. These need to be multiplied. One 162, 306. 162, 306. Okay, looks like we're good now. And then we'll put the real data back in here, make sure we get the right answers again. 8372. 8372, good. 786, 723, good. Okay, so there we go. That's the cleaned up version of the code. Not too bad today. Thankfully, much easier than yesterday. So yeah, good. All right. Well, there you go. There's day 20 in the bag, and you know, fingers crossed that that's actually going to be the tipping point. Puzzles are starting to get a little easier again, we hope, because man, I'm getting exhausted. Some of these here in the middle were really tough. They were not fun. So, all right. Well, hopefully I'll see you tomorrow.